All right, without further ado, we'll get started. Good morning. My name is Graham Stevens. I'm here from KETIV to conduct a webinar here on Introduction to Thin Wall Body Mechanical Modeling using shell elements to speed up your mechanical simulations. So today we are going to talk about finite element analysis modeling of thin wall parts, shell model theory, and then a demonstration of how to set up these objects and what kind of results you might get. And finally, a Q&A at the end. So my name is Graham Stevens. I'm an application engineer here at KETIV. I'm focused on the ANSYS products. I have 25 plus years of experience with product development, consulting, and simulation. And I'm providing application support for ANSYS mechanical, high frequency, and low frequency electronic applications. So when we think about thin walled parts, your ideal quality in terms of mesh quality for a mesh element is a 1-to-1-to-1 block. And when you have elements that are long and thin, whether that's a part that you're then chopping up into smaller pieces to get elements that are long and thin, those long and thin elements, the quality is not good in terms of using them for FEA. So when I have a long and thin part, I have to chop it up into much tinier pieces. And when it's really long and really thin, it turns out that it has to be a huge number of pieces. And so we end up having models that have millions and millions of elements just for this one thin part. So today I'm going to kind of switch back and forth between a couple of different, this presentation and a model. So today we're looking at a block here that's just a cold plate on the bottom. I have a very thin layer right here that is a gasket between the cold plate and a PCB board that happens to be some alumina mounted on top of some epoxy material. And then on top of the alumina, we have a number of chips, which are hot and provide a source of heat. So we're looking at the thermal stress associated with the hot chips on this PCB board mounted, and then looking at, if I hold it down at these points with my bolts, what are different levels of bolt tension due to the stress in the system. And when I look at this system, and especially this very thin layer, it's 0.1 microns thick, I end up having a huge number of elements that are needed. So if I go to this model where I've taken that geometry, sorry, it's starting at mechanical, take another minute or two. What happens is I end up with this very large number of elements that are needed to just model this one part. So if I look at the mesh, my mesh here, the statistics, comes up with roughly 5 million elements, as we saw on this slide. And it just gets intractable, essentially, in terms of actually doing the analysis. So this is what those elements look like. We have we want to have 3 layers of elements, and we we have relatively good quality here at 0.5, but we're still at millions of elements required to just model this one part. So the solution to this is to use what's known as shell elements. And a shell element is a two-dimensional surface that has an associated thickness. So you describe a shell element as a 2D surface with a thickness. And the solid body, that thin gasket layer that we were just looking at, would be replaced by a two-dimensional surface through its midsection with an associated thickness. And when we do that replacement, we're now creating a different kind of element in the finite element analysis model. And these elements, called shell elements, are based on these assumptions. So we have thin shell theory, K through L, that's applied. And it assumes that the thickness is really small compared to the other dimensions. You have at least a 10-to-1 area to thickness ratio or greater, probably 20-to-1. And we have a number of other assumptions. So the material has a high shear modulus, it's isotropic and homogeneous. The normal stress is negligible compared to the other stresses. And the mid-surface has to have a small displacement compared to the thickness and no deformation due to flexion. So for thin gaskets, this can definitely apply. And for a lot of times when you have really thin surfaces, these assumptions apply. And when they do, you can use a shell element. So when I want to then create a shell element, so if I'm now in this system and I'm looking at my brass plate, to create this element within SpaceClaim and change it from a solid body, which it is now, into something suitable to use for shell elements, we can go to the Prepare menu here in SpaceClaim and hit mid-surface. And this, you pick then a pair of offset faces. So we'll pick the top surface and the bottom surface with Control and press check. And now we notice that our solid object, the brass, just became suppressed, and it created a mid-surface 1 brass that now has a associated dimension with it. In this case, 101.6 microns. And so when you do this mid-surface creation of taking your solid body and your solid thin body and creating a section through the surface, and if here, I'll just show you. You end up having, so this is where the mid-surface here has been created, and it's halfway between the two surfaces. So it's splitting your thin body in two, and then essentially eliminating that three-dimensionality, and we now just have a single surface. But when you do that, you have to make sure that you annotate somewhere the thickness. Because when we bring this part back to mechanical, we'll need to specify the thickness within mechanical somewhat separately. So right now, SpaceClaim puts it in the name. That's an easy way to remember it. But do make sure you annotate it otherwise. So now we have our part within SpaceClaim, or we've done the geometry modification that's needed. And so now if I go to this model, we can see that we're looking at the geometry here, and we have all of these are solids. And now when I look at the model, say looking at it here, and I zoom in really closely, we can see that there's no longer a gasket here. We just have a surface that's halfway between the two things it's lying on. So this is what your shell element looks like when it's now created and mixed with solid geometry and 3D parts. Let's now shift to the slides. And we can consider that a shell element theoretically can be considered to be a collapsed solid element. So we can see this solid element on the left, and it's been collapsed. And when it's collapsed, it now has, it's a single little platelet, basically. And now, in addition to movement, translational movement, you can also have rotation for all of your nodes. So you get more degrees of freedom with a two-dimensional body in 3D space. And because of this difference in degrees of freedom, we have to do some different things relative to using it within our model. So the two-dimensional elements are meshed simply as quadrilaterals or triangles. So the meshing of these elements looks like, tiny triangles or tiny quadrilaterals, and they're patch independent. Clearly, when I have a two-dimensional object and I'm meshing it as opposed to a three-dimensional object, the meshing time is much faster because I'm only doing it in one dimension. I've gotten rid of one dimension, and so I have fewer elements to mesh, and therefore my meshing time goes down as well compared to solids. But they're also more complicated because of the degrees of freedom. That shell elements have 6 degrees of freedom compared to solid elements, which have 3 degrees of freedom. You have to use what's known as MPC contacts between the solid and the shell elements to bound these rotational degrees of freedom and allow the model to work well. In addition, when we create that two-dimensional mid-surface, and we're doing a contact between the body, the thin body, and something else, we need to specify, are we talking about the top surface of the thin body or the bottom surface of the thin body in terms of what another solid is contacting to? So there's a little bit more extra setup in terms of contacts that are needed for shell elements. So I will demonstrate that in the model in a second. So we go back here. So for the contacts here, for the connections, I'll just go through some of the connections for this entire model. So we have the chips to alumina, and where we have solid objects to solid objects, and we're just using bonded contacts here. So we have this chip on top of the alumina, and if we look closely, we see the red area where it's contacting, and it's contacting the face of the alumina board, and all of these are similar. So that's your standard bonded contact, solid object to solid object. But then when we look at our base plate to screws, again, we have solid objects here where we have the screwing into the base, the cold plate here. And so we have a contact of the whole of the base plate to the screw. Again, solid, standard bonded contact that you're used to using solid objects. When we start looking at the now looking at the screw and how it contacts the brass gasket, we have a slightly different contact structure. So we have the outside of the screw surface, as you would see for a solid body, but now we need to contact the edge of this two-dimensional surface. And so that's how we specify this, and it's nodes on edge. And then for the formulation, we need to specify MPC here. And then we also need to specify the constraint type distributed all directions, which I'll cover in a moment. And so for each of these, anything that contacts that is in contact with your two-dimensional shell object now needs to have MPC contacts and has to use this constraint. You have restricted number of restraint types, which I'll get to in a minute. So so this screws to base head plate is just sort of the bottom of the screw head to the top of the base plate, and that's a solid connection. And then we also have when we're talking about now the cold plate here, which is contacting the gasket, which is here, we have to tell the computer which we have the top of the cold plate, but now the gasket we know is a two-dimensional surface, but we have to tell it, is it the bottom surface or the top surface? So another thing that we have to specify when we have two flat contacts is whether we're contacting the bottom surface or the top surface. And so you can see if I say the top surface, we can sort of see the top of this is being contacted and the top of that. So that's not actually the contact we want. So you have to go back and check this visually is sort of the easiest way to do it, where now we can see that if I look underneath this gasket, I'm getting the red area here, opposite the blue area here, as we sort of zoom in between these two objects. And that is the correct way that you'll see these contacts sort of showing you the right sides. But you need to make sure that you've done that properly, or you won't be able to, it won't solve properly in terms of the contacts. So this is just one other additional complication on the contact side. So the shell element will reduce the total number of meshing, total amount of meshing you need to do by a large quantity, but it also requires a fair bit more setup in terms of contacts. So that's sort of the disadvantage. So I mentioned the MPC constraint type. So the MPC constraint type, which is underneath the advanced area into the formulation, there's constraint type. And essentially you need to specify a distributed connection, whether it's normal only or all directions or anywhere inside pinball. You can go to the help for more on this or refer to the wall of text here, my apologies. But essentially, typically I'll just use distributed all directions in general, and then but the projected types only couple translational degrees of freedom, so you can't use projected displacement or projected uncoupled U to ROT for the constraint type because of these degree of freedom considerations relative to solid versus shell elements. So in addition to a shell element, there's another body called a shell solid element that is sort of in between solid elements and shell elements. It is a three-dimensional element. It's also intended for thin structures only. It has the same structural degrees of freedom as the solid element, so it's a little easier to work with constraint from a contact perspective. But a solid shell element is required to be mesh sweepable. So when you sweep a mesh, when you have a sweep mesh, you're sweeping the body from one side to the other, and the sort of beginning surface that you start the sweep and the end surface that you end the sweep have to be the same size. And so that means you have to use relatively simple elements, but I wanted you to be aware of this other solid shell element option as well. It's sort of intermediate in between shell elements and solid elements, and has its own sort of mesh. If you have mesh sweeping available, it can be another good option. So I just wanted to be aware of that. And then another issue, of course, associated with solid elements is that when you're using linear quad elements in particular, If those linear elements don't accurately model the curvature bending and curvature present under bending, it can introduce an artificial shear stress. And you avoid that shear locking phenomenon by using shell elements or by using solid shell elements. The other thing you need to do with shell elements to use them is to turn on the solver settings under solver controls, the large deflections, because due to the thin, flexible bending characteristics of the shells, large deflection effects can become important. The shell may stiffen with deformation. And so to properly account for this, you have to turn large deflection effects on. And similarly, because of the slight differences in terms of force and moment quantities, if you're looking to use those in user-defined results, you may want to turn on the general miscellaneous output controls to enable post-processing for those particular options. So with those caveats, essentially now I've taken my mesh, which was in the 5 million range using a solids model. And now I have very good element quality here where, most of my mesh is in the 0.95 range. I've cut off I don't have any elements less than 0.2. And if I'm scrolling in, now you can sort of see, instead of having 3 thin layers with a lot of elements here for this brass layer, which is just a 2-dimensional object now, the mesh is much less refined, as well as the objects, or the aspect ratio is also it's definitely not 1-to-1, and that allows you to get away with a lot less mesh. So let's just turn all the bodies off and take a look at that mesh just so you get a sense of that. And this is, this mesh compared to the other, the other mesh I had here. And so you can see you have many fewer mesh points. That means I don't have to mesh all that extra mesh. It's much cleaner and faster to run this model. So the total mesh statistics for this body now are in the 1500 realm, whereas before it was in the 5 million realm. And now I have the total mesh for the entire model is only 400,000 nodes, or 86,000 elements. And so the model runs much faster. And so then just to take a look at here, let's show all the surfaces again. For the steady state thermal analysis that we were doing here, I was putting some extra heat in to represent the chips and what kind of heat they're exerting, what kind of heat's coming out of them, and then doing a cold plate here, holding it at a constant 25 degrees to get our thermal profile here of what this system is looking like. And similarly on the structural side, I can put in bolt pretension, a fixed support at the bottom, and look at the total deformation for this system as well. One kind of quirk as well that I wanted to alert you to, especially for multiphysics and this kind of modeling, where I am taking the results of my thermal analysis and using that as an imported load into the structural. And when you do that for this imported load, a quirk of this is that you have to import the load in two pieces, essentially. So you'll get the load here when you do the porting over in Workbench. You'll have the load, but it won't resolve because you'll have a mixed 3D or 2D object within the load. And so to handle that, you need to right-click on imported load, insert another body temperature object here, and then for that object, you need to go back to the geometry and select all the 3D solids for one and all the 2D solids for the other. So this is the 2D solid, happens to be the brass gasket, so that these imported loads can then resolve with separate dimensionality, essentially. So just be sure that you separate the dimensionality when you're doing that. When you're doing this kind of mixed, bringing the body temperature in from my steady state thermal analysis in as a load condition for the static structure. And so with that, that's just a brief overview of this arena in terms of using shell elements to save yourself some time. I just wanted to sort of open things up for questions now. If anybody has any questions, please feel free to put them in the chat. The use of shell elements or shell solid elements can allow modeling of thin wall structures, which would otherwise need a prohibitively large number of mesh elements to accurately model. And that can definitely speed up your simulations. If you're interested in diving into more details about this, please do take advantage of the ANSYS Learning Hub, where there's a relevant course called Beam and Shell Modeling. There's also some, the ANSYS YouTube channel has tutorials. There's a tutorial called Beam and Shell Modeling with ANSYS Mechanical. Beam elements are similar to shell elements, but instead of being a simplification in just one direction within direction, the beam element is a simplification in two directions, where you have basically a line body instead of a two-dimensional object, and with similar constraints with regards to needing to do some different things in terms of matching constraints as you're using those, mixing the solids. And then, of course, as usual, at all times, please do reach out to support@ketiv.com or our 800-866 number 465-3848 if you need further support, in particular with regards to your particular case. Make sure you're aware of that and reach out to us if you need help. KETIV does simulation services as well for ANSYS in the mechanical, fluid, and electronic realms. So if you're looking for some help to actually execute work, we do it all, you do it all, or anything in between. So we can help mix and match. We can teach you on your parts. We can do it all for you, whatever makes sense in terms of simulation in these areas in ANSYS. And then finally, I wanted to mention our upcoming events. Next week's KETIV Virtual Academy is called 3D Printing with the New BOSS and SnapFit Tools in Product Design Extension. And this is a Fusion 360 product design extension that Brian will be going through the BOSS SnapFit tools. And he's looking at 3D printing and enclosure for a PCB board. So if you're interested in that for next week, that's please register at ketiv.com//learn. Relative to ANSYS, please do next month, August 25th, there'll be another KVA that's ANSYS related with a session focusing on optimizing your medical device manufacturing. So please stay tuned for details on that. With that, I think we will wrap up. Thank you so much for your time and attention, and have an awesome day.